First of all, I will say welcome to this GRASS webinar, Smart Speaker Testing. My name is Ole Theilgaard. I'm Director for Global Support and Applications at Audio Precision and GRASS Sound and Vibration. I will be the presenter for this webinar here this morning and also for some of you this afternoon. So yeah, we will actually just jump into it and start. See, today we are going to look at smart speaker testing. So we will actually first of all start looking at the speaker itself, have a little talk about that. Then we will have a look at the recommended standard. Every time we are going to test something, then we have to test it according to the different available standards. Then we will look at what type of test do we have to perform. We can do electrical tests on some of the components. We can do acoustical tests on others of the components. We can do open and closed loop tests, and we will have a little talk and discussion about open and closed loop tests. Then we will look at the different challenges when we are going to measure. What do we have to look at before we are doing the measurements? We will look at the recommended equipment, and in the end, there will hopefully be some time for questions and of course answers. During the presentations, then you are free to use the Q&A chat function in here in Teams for getting your questions, and after we are finished with the presentation, then I will go to the Q&A function and answer all the questions. Okay, let's start. Speakers. Yeah, first of all, a little definition of the speakers. We have actually something we call speaker units. It's actually the little speaker itself, the component we use to build in to the speakers we have back home in our television, whatever. And for speaker units, we do actually have different types of units covering different frequency ranges. For the low frequency, we have a woofer, typically covering from 40 Hertz to about 500 Hertz. We have mid-range speakers covering frequencies from about 250 Hertz to about 2 kilohertz. Tweeter covering the high frequencies from 2 kilohertz and up, and then we have some full range speakers covering as much as possible of the audible frequency range. As I mentioned, these speakers or these speaker units, they are actually used as subcomponents for producing the speakers we are using back home. It could be passive speakers. The passive speakers, they require an power amplifier and an externally power amplifier. Have active speakers where we have built in a power amplifier together with the speaker units. Wireless speakers, smart devices, Bluetooth or Wi-Fi speakers, also with built-in power amplifier. Today's subject is smart speakers. So let's look at the definitions for a smart speaker. A smart speaker is a wireless speaker with a voice command device with an integrated virtual assistant that offers interactive actions and hand-free activations with help on one command, one hot word, or several commands, hot words. So let's have a look at the standards. Most important standards when we are talking about speakers is actually the IEC 60268, the one describing sound system equipment. Especially part 5, the one which actually describes loudspeakers, is the one we have to look at when we would like to test speakers. When we are doing tests of speakers, doing especially tests of smart speakers, then we also have to have a look at the IEEE standard 1329, which actually describe a method of measurement the performance of a speaker phone. And smart speakers is actually very, very equal when we're looking at the standard to a speaker phone. We also have to mention the ITU, that's T recommendation P51. This is the standard for the artificial mouth, which we also are going to use when we are testing smart speakers. Also, we have to mention the IEC 61094, that's 4. This is the measurement microphone standard. The IEC 60268, that's 5. It would actually point at the IEC 61094, that's 4, when doing the acoustical test of a speaker. But doing the acoustical test, we need a microphone, and this microphone has actually to fulfill the measurement microphone standard, the IEC 61094. If we look at the test standard for smart speakers, then if we go through all the standards, then we can't find any standards who actually in details describe how to test a smart speakers. But as mentioned before, the IEEE standard 1329 from 2010 describe a method of measuring the transmission performance of speakerphones. And this standard is actually the one most of smart speakers manufacturers actually are using today. The standard is, or the test setup in the standard is actually like what we have here on the drawing. We place our device on the test, the loudspeaker, the smart speaker, on a surface, and a table surface in the middle, and then we actually place an artificial mouth 40 centimeter and 30 away, and in a height of 30 centimeter above the smart speaker on the test. We do the same with the microphone. In this way, we are actually able to test the performance for our smart speaker. If we do this setup, then we will actually cover a frequency range from about 200 hertz and up to 20 kilohertz. Normally, when we do this test, then we will have a level from the speaker itself around 94 dB. The level from our artificial mouth is about 89 dB sound pressure level at the mouth reference point. Is actually just in front of the artificial mouth itself. If we look at a block diagram of a smart speaker, then it could actually look like this, where we have different interfaces. We could have a Wi-Fi interface, we could have a Bluetooth interface, we could have a LAN interface, a cable interface with LAN, we could have a USB cable interface as well. All these interfaces will go directly to the audio processor and master control unit, where we can have a wave file either coming in via the Wi-Fi, Bluetooth, the LAN, or the USB interface. We also have a user interface for controlling the buttons we are pressing, giving us some indications of the configuration, the setup, if the unit is powered up and things like that. Of course, there's also a power supply and a battery management block, giving us the different power and voltages to drive the whole system. Then there might be an audio input where we can have a cable input, where we can connect our telephone or whatever and play music via a cable, via the audio processor to the speaker. And then we have something we call a voice input. The voice input is actually a microphone. A microphone which actually will pick up the noise and the speech around the speaker. If it is the voice, then it will actually trying to decode this voice, and if it finds something which is reasonable, which is actually part of the whole speaker itself, then it will start doing some commands. So in the smart speakers, we have actually the voice command. It will come in via this voice input via a microphone directly to the audio processor, and the audio processor will actually, depending on the commands coming in, do something different things. It could be that if you ask it via your commands to search on the internet for a special kind of music, then it would actually start searching on the internet for this music, find it, and then it will start playing this music. The master controller, amplifier, and in the end, a speaker unit, so we actually can hear some music from this smart speaker. If we look at the different tests, then we can actually divide the test up in two. We can divide it up in electrical test and acoustical test. We will start with the electrical test. With the electrical test, then from a generator, from an analyzer, we will send in an input stimuli, a frequency, a voltage, and then we will measure the output response of the block of the device. So we can actually do a test of our voice input, because we can actually replace the microphone or the microphone array with a generator signal, And in this way, we will actually be able to test the analog circuitries in our voice input, as well as the digital circuitries. So we will actually, with different audio analyzers, be able to test today, to do an electrical test of the whole voice input module. With the audio input, exactly the same. We will put in a stimuli and we will measure an output response. And again, the same with the audio amplifier. We will put in a stimuli and we are able to measure an output response of our amplifier. Normally when we are testing only the amplifier, then we have to remember to have a load on the amplifier. So the amplifier will see the same load as when it was loaded with a speaker unit. We also have possibilities for doing acoustical test, block test, or component test. With an acoustical test, then we use an acoustical signal as the stimuli, and then we measure an acoustical response or an electrical response from the device. In this way, we have the possibility for controlling the whole voice input by applying an acoustical signal to the microphones and then measure the output. We can do exactly the same with the amplifier. We apply an electrical signal to the input of the amplifier and we measure an acoustical response on the output. We can also do it on block level. If we look at the audio amplifier, including our speaker, then we actually make a measurement setup like the one we have here on the picture, where we have an audio analyzer. The output of the audio analyzer will control the input of our audio amplifier, and then we will place a microphone in front of our speaker. The microphone will normally be placed, if it's a speaker unit we are testing, in a distance of about 1 meter. Of course, it depends a little of how big this speaker is. If it is a smart speaker, then you might go a little bit closer to the speaker, so the distance is closer. So in this way, we are measuring frequency response. We are also measuring the sensitivity, and as mentioned before, the sensitivity is normally measured in a distance of 1 meter. We are also doing different distortion measurements in this way. If we look at block level test of the voice input, it's a test of our microphone array. Then it's actually very similar to what we saw before. In this case, we are actually using a mount simulator for creating the test stimuli, creating the test signal for our microphone array, and then we will measure the response of this microphone array on the output of our voice input. In this way, we are able to measure sensitivity, frequency response. We can also do distortion measurements, both totally harmonic distortion, total harmonic distortion plus N, rough and bust. There are many different measurements, distortion measurement, which can be performed this way. Another important measurement we're actually doing in this configuration is actually a directivity measurement of our voice input of our microphone array, because it is very important when you have a smart speaker that it's not depending on where you actually are standing in front of the speaker before it actually will react. So it doesn't matter if you are standing, so to say, face to face, or in an angle of 90 degree or 180 degree or whatever to the speaker. The speaker should actually be able to recognize your voice and recognize the different commands you are trying to send to the speaker. It should not be depending on where you are in front of the speaker. So therefore, the directivity of the microphone array is very important. We can also do a test at component level. In this case, it is actually a test of the speaker unit itself. With the speaker unit itself, we are of course interested in frequency response, distortion, and sensitivity of the speaker. We talked before about speaker response. We talked about distortion and also sensitivity, where it is important that we have a certain distance between the speaker and our pickup microphone, the microphone which actually will pick up the response from the speaker. But another very important parameter to measure on the speaker units itself is the impedance of the speaker, because for the speaker unit itself, you need to know how the impedance is, because it has something to do with the type of amplifier which you would use for driving the speaker. If your amplifier can't drive the speaker you have selected, then the whole speaker, the whole smart speaker, will probably not fulfill the requirement you have set up during your development phase. Therefore, the speaker impedance is an important parameter. And to measure the speaker impedance, you make actually a setup like the one we have here, where you have an amplifier. Is actually the one called 12AU output section. It's a power amplifier. In this power amplifier, you have a little sense, a little current sense resistor. Is actually the one we have marked here. This resistor will sense, actually measure a voltage, but we are also measuring the voltage across the speaker, and in this way we are actually able to calculate the speaker impedance. So we can calculate the speaker impedance as a function of frequency, because it will actually change over the entire frequency range. Component level test of a microphone array. Yeah, it's very similar to the setup we saw before. And in this way, we are going to measure sensitivity, frequency response, phase response, because we might have more than one microphone in our microphone array. and for making beamforming techniques, for having the right directivity, and to get rid of some of the background noise, then the phase response or the phase difference between each of the microphone in the array is very important. So therefore, it is important to measure the phase response as well. Distortion measurements is also measured. Again, yeah, we use an artificial mouth as the input, as to generate the stimuli, to generate the test signal for the microphone array. If we are going to make a full test of our smart speaker, a full test as we actually do it in the production line, then it is actually a setup like the one we have here, where again we have a mouth simulator for sending in commands and test stimuli to our microphone array in the speaker. We have a microphone for picking up the output of the speaker, measuring the frequency response and sensitivity and all these parameters. And then we have but for doing this, we need actually access to wireless access or cable access, normally wireless access with a smart speaker. So we need either a Bluetooth connection to our test equipment, or we need a LAN or wireless LAN connection to our test equipment, or it could also be wired via USB or a wired LAN connection. When we do this, we will come back to these tests on the next slides. When we do this, then we are able to test the speaker sections. And again, it's the same parameters as we already have discussed. It's level or sensitivity, it's frequency response, it's distortion measurements, totally harmonic, robust, and directivity measurements as well. For the microphone section, we are actually going to measure very, very similar parameters. See, when we are doing tests, especially on smart speakers, then we actually have different way of doing these tests. We can either do it as a closed loop test, where we have made a wired connections, a directly connections between our test equipment and the smart devices on the test. So in this case, you can see we have a cable connections from our audio analyzer directly to the smart speaker on the test. So we actually can, so we have, and we are using the direct input on the smart speaker for doing this test. The setup with our microphone is according to the IEEE 1329, where we placed our microphone 40 centimeter away in a height of 30 centimeter above the smart device. We do exactly the same with our mouse simulator, 40 centimeter away from the device under test in a height of 30 centimeter above the device under test. In this way, yeah, we can do a full test, a full closed loop test of our smart speakers. But in most of the cases, we don't want to do cable test. We would actually like to do it as an open loop test. Open loop test means that we actually load a file. It could be a WAV file, which normally is done on a smart speaker. So we put in a WAV file or load the smart speaker with a WAV file, and then the smart speaker will start playing this WAV file, and then we will do our measurements on this test signal we have in the WAV file. This WAV file will be loaded into the smart speakers via Bluetooth in this case, where we call it a simple loop test. When you do this, then it's actually a good idea that before you start your measurement that you have a pilot tone, a trigger tone. So you tell your analyzer that in a few seconds we will actually start with the test, with the really test signal. So it's actually a trigger. The pilot tone here is a trigger it's a trigger telling the analyzer now we are actually ready to do the test. And then the chirp signal, where we have a frequency sweep, will be added, and then we will make a frequency sweep of the device and measure the response, the output response of the smart device with this input signal. We can also do what we call open loop test, not the simplified one, but a really open loop test. It's actually where we actually use the internet or use a server. So we have access to the server from where we actually, or the internet, from where we will get our test signal. The configuration is very similar to what we actually saw before, but in this case, we will actually be able to do a full test from sending in a command from our audio generator via an artificial mouth, telling the smart speaker, now you have to execute this command. The smart speaker will start executing this command. In many cases, it will actually create connections either to the server or to the internet, and then it will on the server or on the internet find the file we have asked it to play, and then it will actually start playing this file. If we look at it, the command flow, then first of all we will to the smart device send or tell it, or give it a wake up word. After the wake up word, we will actually send a command to it. And after we have sent a command, then the smart device itself will actually decode this device and decode it and actually use either the internet or the server, and then it will use the intelligent virtual assistant for finding out what to do. in many cases, you are probably asking the device to download special types of music, a special test signal when we are doing test. Then it will actually find the file and then in the end play the file. For the most common speakers on the market, Google Assist, then we will actually start with Google Assist as wake up word. Amazon's the wake up word is Alexa, and for Apple's the wake up word is Siri. So we will actually start with Alexa, play test file number 1. Then in the IVA, Intelligent Virtual Assistant server, it will actually find test file number 1, and then it will be played. When we look at it on time, in a time domain, then we have the wake up word together with our command, and then the next text sequence is again a pilot tone, because we don't know the time difference from the smart speaker getting the access to the internet, downloading the file, and then start playing it. So we need actually the pilot tone for telling the analyzer that in a few seconds you will actually see the really test signal. So again, the pilot tone is a trigger, and then we have the chirp signal, our sweep signal. So the wake up word is for making the configuration and set up the smart speaker to execute the right sequence. Pilot tone, trigger for our analyzer, and the chirp, the test signal, sweep sign, a noise signal, white noise, pink noise, things like that can actually be used. Challenges when we are doing measurements. We talked actually before about GHD measurements, and especially when we are doing rub and bus measurements, where we have a fundamental frequency, normally low at lower frequencies, and would actually like to see the performance at higher frequencies. Normally we would like, when we are doing rub and bus, we would like to see between the 14th and the 20 harmonics of the fundamental frequency. When we are doing these TDH measurements, it is actually very important that we have selected our microphone so it will actually cover the expected range of interest when we are doing these measurements. And here we are actually talking about the dynamic range. So the self noise or the inherent noise of the microphone aren't too high. If we look at the graph we have here, then we can actually see that the self noise or inherent noise of the microphone we are using in this case is about 40 dB. So we have an inherent noise of about 40 dB. And if the signal we apply from the speaker, our test signal, is actually the yellow one. We can actually see that at some frequencies, the yellow one is below, much below is much below the noise or the self noise of the microphone. So what we actually measure, it's the red line, is at frequencies where the yellow one is below the green one, the inherent noise of the microphone itself, then we will not be able to, with the microphone, to measure below the self noise of the microphone. And therefore, our measurements is we will actually measure at 2, that the total harmonic distortion will in this case be too high. It will not be correct because we will actually measure the distortion of our microphone we are using for doing the test and not measuring the distortion of the speaker or item we are going to test. If we look at it, then the signal to noise ratio between our fundamental and our noise floor, it should actually be at least 40 dB. I will actually recommend 46 dB. 40 dB if we would like to measure, if the minimum distortion we would like to measure is about 1%. If we would like to measure a minimum distortion down to 0.1%, then the ratio between our fundamental and the noise floor of the microphone itself should be at least 60 dB. To add an extra 6 dB signal to noise is a very good idea. So therefore, we will actually recommend that you go for 46, 56, or 66. At least add a 6 dB more to get a more accurate measurement. See, when we are doing a test of smart speakers, then it's also important that we are looking at the sound fields for selecting the right microphone and actually measuring the right response from the speaker under test. If we look, then in most cases, when we are doing a measurement of a loudspeaker, then we have the speaker, the source itself. We have, and then in a certain distance, we will actually place a microphone. In most of the cases, we will actually place what we call a free-fill microphone in front of the speaker, because normally we are placing the microphone in 1 meter or also closer when we are doing these smart speakers testing, then and do it according to the IEEE 1329. Then we place it in a distance from about 40 centimeter from the source. If we look at different sound fields, then we actually have what we call 3 different sound fields, or main fields, I will call it. We have our near field, is also called the pressure field. In the near field, then it doesn't matter if you move your microphone a little away from your source. then you will actually still measure the same level, the same SPL level. And then the more you move your microphone away from the source, then you will probably start measuring a little bit lower, but actually not much. At a certain level or a certain point, then you will actually see that every time you double the distance between your source and your microphone, every time from each measurement, then the output of your microphone or the SPL level you are measuring with the microphone will drop with 6 dB. When it starts doing that, then it's because you are in the free field. And in the free field, you are using a free field microphone. You will be in the free field for many, many meters distance to your source. If you do it inside a room, then at a certain distance from the source, then you will be too close to a wall, and then you will have reflections from the wall. It's also called the reverberant field, where everything actually starts again to grow up, so that you will not see that the sound pressure level is decreasing for each time you move your microphone, but it will more or less be the same. The transition between near field, pressure field, to free field is typically about 1/3 of the longest wavelength in your signal. So you have to look at your lowest frequency, and then you have to take the about 1/3 of that wavelength, and then you would actually get your frequency. If we do the IEEE 1329 measurements in a distance from 40 centimeter and 30 centimeter of height from the source, then you will be able to, then the transition in this distance is about 200 hertz. So you about 200 hertz, then you will be in the free in a free field environment at this distance. Yeah, and when you go from free field to the reverberant field, then it's typical 6 to 10 dB higher than the reflecting sound. So we will actually start using a free field microphone in this environment, because in a free field environment, a free field microphone will actually have a very, very flat frequency response. If we look at the upper curve here, the one is black. I have my cursor around it now. It is actually the frequency, the free field response from this free field microphone. And you can see it's very flat. So it's actually, it will not have any influence in your measurements. But if you move your microphone closer to the source, so you actually will start working in the near field, then the microphone will actually start acting like a pressure microphone, and it will actually measure the sound pressure level with its pressure in a pressure field, and it's actually the one is the gray curve we have here. So it's the pressure. So you can actually see at higher frequency, we will measure a lower SPL signal with a free field signal. If we are too close to the source, because the microphone will actually measure it as a pressure microphone. So we talked about free field, we talked about near field pressure measurements. See, we could also change the microphone to a pressure microphone. And if we do so, then we have, of course, have to look at the pressure field. So if we change the pressure microphone, and now if we place the microphone very, very close to the sound source, then we can see that we have where in the near field where we have the pressure field, then we can actually see on the graph here that the response for the pressure microphone is very, very flat in the entire frequency range from that microphone. But if we move the pressure microphone away from our sound source, so we actually will go from pressure field to free field, then something will happen, because we will actually start building up pressure at higher frequencies in front of the microphone, because the microphone will actually disturb the field in which we are operating in. And it will actually disturb the field, as we can see that we will actually with a microphone like this about 20K, then we will measure about 5 dB higher sound pressure level for the microphone. So the pressure microphone is not a good microphone to use in a free field. But we can actually do something with this microphone, because we can actually turn it around. So the microphone will not point directly at the source, but it will actually be, it will have a 90 degrees incidence angle to the source. If we do so, then if we look at the graph here, at the light blue here, then we can actually see that we will have an almost flat response up to 20 kilohertz. So a pressure microphone, if we would like to convert a pressure microphone into a free field microphone, then we have to use it in 90 degree incidence to our sound source. Solutions to the different challenges, front ends and test of the speakers. Yeah, we can use a free field microphone like the Grass 46 AE, covering frequencies up to 20K, large dynamic range from 17 dB up to 180 dB. You can also use a pressure microphone like the Grass 46BL. It's a quad-inch, covering actually the same frequency range as, almost the same frequency range as the free field microphone. It has almost the same noise floor and upper dynamic range. And yeah, for microphones, you need a power module, and yeah, you can use a 12AQ from Grass, and when you are working with microphones, then you also need a calibrator. So in many cases, you also need a calibrator like the Grass 42AG. And other challenges is actually the mouth simulator. The mouth simulator, it should actually give us a standardized test of our voice input. And it should actually be a sound source which simulates the acoustical field close to the human mouth. A mouth simulator fulfills the standards written here, the IEEE 269, the IEEE 661, and the ITU-T recommendation P51. And for fulfilling these, then it's required, first of all, a well-defined frequency free field response in near field as well as in far field. If we look at a mount simulator, then the mount simulator, the parameters specified in the standard is free field response, it's abstraction diffractions, where you are measuring in a certain distance from the mount, 0.5 meter. Then you are looking at maximum sound pressure level, distortion, and of course linearity. Yeah, and all these data are of course available from different mount simulators. If you look at the response here, the green curve, then you will actually see that it's not a flat and nice curve. No, because the mount simulator is actually very, very equal to a speaker, and no, you can't get a speaker which is 100% flat. So what you actually have to do with your mount simulator is actually you have to equalize your signal, so you will get a flat output response from the speaker. It means that you will have the same energy at all the different frequencies. So you can perform your test with a well-known reference level. So why actually using a mount simulator and not just a standard speaker? First of all, the mount simulator, it fulfills the standards. The mount simulator has a documented test report. You have to use it for R&D tests, and of course for your test approval, for your approval of your smart speaker. You can of course use the mount simulator in QC test and also for production test. In some productions, you could also use a standard speaker because you have made your type approval based on a mount simulator. So for your production test, you could use a speaker and just have a transfer function between your speaker and the mount simulator. So you can use it in your production for the final production and for QC test in your production. For smart speakers, the solutions, from Grass, we are providing 2 artificial mount simulators, 44AA and 44AB. The 2 speakers are more or less the same. The main difference is that the 44AA is delivered with a built-in power amplifier, while the 44AB needs an externally power amplifier. Else the performance for the 2 devices are exactly the same. For doing calibrations of these, then you need a reference microphone. A reference microphone which will be placed in a test jig in front of the simulator, simulating the mount reference point in which you actually made your calibration of the simulator. When we are doing measurements, then the measurements are in some cases disturbed by the background noise, or we will actually disturb the environment around us. So for get rid of this problem, then we can actually place our speaker on the test into a test chamber. It means we can actually do test of our microphone array into a test chamber. We can do test of the speaker unit itself into a test chamber, or we can do a test of the complete smart speaker into a test chamber. If we're doing, and this is if we are doing a production test and we don't want the different production lines to disturb each other. A test chamber, acoustic test chamber, like the Grass AL30, can actually be used for this purposes. Conclusions. When doing a smart speaker test, we have to do the test according to the standards, the ISE 60268-5, IEEE 1329 from 2010, ITU, that's TP51 for our mouth simulator. For the microphones, we have to have in mind that we have to select a microphone with the right dynamic range. Especially, we have to look at the noise floor or the inherent noise of the microphones itself. It has to be as low as possible if we would like to do good total harmonic distortion measurements. We have to look at the frequency range. We also have to do free field or pressure field, near field measurements. In near field measurements, we have to use a pressure microphone. In far field measurements, we have to use a free field microphone. The mouth simulator has to follow the standard. A test box is recommended if you have many production lines close to each other, so you won't disturb the different lines. There was actually the words, and let's go to see if there are any questions. I cannot see any questions right now, but maybe they are coming up. No, it doesn't look like that there are any questions. I will wait 2 minutes. Maybe some questions will come up, and then I will answer these questions. In the meantime, I will take some tea. We have one here. What will the process be for measuring directivity patterns, both of the acoustical output of the microphone array? See, for measuring the directivity, then you need either the microphone array to be turned around. You could actually use a turntable, so the microphone array will actually turn around your speaker, your reference speaker, your mouth simulator, and in this way you will be able to measure the different angle of incidence for your microphone array, and in this way you will be able to measure the sensitivity at different angles, and then you can start correlating and find out if the sensitivity is okay for your microphone array. Maybe you have to add some extra microphones to be able to do something. And then we have one who's asking about open loop testing of smart speakers through the cloud. When testing through cloud for smart speakers, would you want to add the test file to our music playlist and then do testing? Yes, when you do test via the cloud, then your test signals, they should actually be placed in your cloud, either on your own cloud server or on the available server, Apple, Google, and Amazon's. I know that from some of these huge companies, it's difficult to upload test signals and upload your own music. So it's actually possible to play it that way. And in these cases, you have to do it via a local server. And then another question, same person with another question. With the wake up word, is AP program with the wake up word and command using the mouth simulator, or would you want us to say the wake up word and command? When doing these tests and doing these tests automatically, then you have to program it into the AP analyzer. So we do not have the different wake up words directly in the analyzer, but you actually have to record it. You have to record a WAV file. Then you can play this WAV file via the analyzer. So you have to wake to record a WAV file. It could be Alexa. Then you have the wake up word, and then you record Alexa. Wait a little, and then you tell Alexa the command, please play test signal number 4. And when you have done that, then you have to upload on your server a file called test sequence or something like that, number 4. And then it will actually find that test sequence on your server and then start playing it. In the test sequence then you have on the server, then you have to play in your first your pilot tone, and then your test signal, your sweep or whatever you are using. And then we have one here. Why is the test stimuli level different to the test microphone versus the speaker? 94 dB and 94 dB for the speaker and 89 dB SPL for the microphone. The test level is different because the standard is actually looking at when you are speaking or talking to somebody, in this case the smart speaker, then you will actually not talk that loud. So therefore the level is less. With speakers, the it has actually in many years been a standard that you do the sensitivity measure the sensitivity at a level of 94 dB. So the 94 dB is actually what we actually have been doing in the past and doing according to the IEC 60268, while the 89 dB for the microphones is due to the fact that we are not speaking that loud normally.